All right, so we talked about TLS, which actually resides in application layer but provides transport layer security. Now we are moving one layer below and go for network layer security, which is called IPsec here. So we will talk about IPsec protocol. Provides datagram level encryption, authentication, integrity for both user traffic and control traffic. For example, BGP and DNS messages. So there are two modes. In the transport mode, you have the payload here. So as you can see, we are going to talk about routers here because we are going to have the encryption at the network layer. So in the transport mode, only datagram payload is encrypted, authenticated, like this. In the tunnel mode, the entire datagram is encrypted, authenticated. Encrypted datagram encapsulated in new datagram with new IP header, tunnel to destination. So this is actually what we use in VPNs and so on. Here you have the payload, then encrypt everything. Okay. So there are two IPsec protocols. One of them is shortened as AH, and the other one is ESP. Authentication header protocol provides source authentication and data integrity, but not confidentiality. Okay, so this is not much used. But in the encapsulation security protocol, this one provides source authentication, data integrity, and confidentiality. So this is why it is more widely used than AH protocol. So here we need to talk about security associations. So because in the routers, we have to keep some tables, and this way we have to understand which data should be encrypted and so on. So before sending data, security association established from sending to receiving entity, like in this picture. Ending receiving entitles maintains state information about SA. Recall TCP endpoints also maintain state info, but IP is connectionless. So this is why IPsec is connection oriented. We have to keep, which IP addresses are communicated in an encrypted way and so on. Right? So R1 stores for SA. So by R1, it means this router 1 here. Okay, this is R2. So R1 stores for security associations. So it stores 32-bit identifier, security parameter index, SPI, origin SA interface, this IP, destination SA interface, IP of the second router, destination, type of encryption used, encryption key, type of integrity check used, authentication key, and so on and so forth. So you have to store all of this. So this is why we say it is a connection oriented. Okay, let's look at an IPsec datagram. So you have the original IP datagram payloads. So recall that in the ESP tunnel mode, we encrypt everything. So in the AH mode, we didn't have encryption. So this is your original IP datagram payload, original IP header. So you put ESP trailer here, which contains padding, pad length, and next header. Okay, you encrypt this part. Okay, then put ESP header, sequence numbers. Then take the calculate the MAC of it. So this is why it is authenticated. So recall that we put sequence numbers here. This is the same as we did in TLS to prevent packet ordering attacks. So now, since all this part now looks like a new datagram, so you have to put new IP header because now the length is increased and so on and so forth. Okay, so for the outside world, this just looks like a ordinary datagram with header and the payload, but the original payload is here, and this everything is encrypted and so on. Okay, let me look at the slide to see if I missed anything. Yes, sequence numbers toward replay attacks. Yes, we already mentioned this. Okay, let's look at actions of the ESP tunnel mode. Yes, so the payload comes from the application layer. It moves down to network layer, and router 1 appends ESP trailer to original datagram, which includes original header fields, encrypts results using algorithm and key specified by SA. So initially you have to put secret keys and algorithms there. Mostly used algorithms, AES here again. Appends ESP header to front of this encrypted quantity. Creates authentication MAC using algorithm and key specified in SA. Appends MAC forming payload. Creates new IP. So this is the MAC, by the way. Creates new IP header fields addressed to the tunnel endpoint. So because now you are sending to this part, so your IP address is mapped to here, right? There it will be decrypted and then will send to the destination. IPsec sequence numbers for new SA, sender initialize sequence number to 0. Each time datagram is sent on SA, sender increments sequence number counter, places value in sequence number field. So this is why it is connection oriented. Goal is to prevent attacker from sniffing and replaying a packet. Receipt of duplicate authenticated IP packets may disrupt service. So this way you prevent them by the sequence numbers. Method, destination checks for duplicates. Doesn't keep track of all receipt packets, instead uses a window. Okay. So IPsec security databases contains two parts, SPD and SAD. So this is security policy database. This is security association database. So one of them, this one actually dealing with how to do it, but this one dealing what to do. Okay, so let's look at SPD. Policies for given datagram, sender needs to know if it should use IPsec. Because just by looking at the destination, they can, from the table, it understand if it needs to be use IPsec or not. Maybe you are sending traffic to ordinary internet, or maybe you are sending data to one of your workers, which is now in a hotel abroad, and you want to communicate in an encrypted way. So you can think about VPN scenarios here. So policy stored in security policy database needs to know which SA to use, may use source and destination IP address and protocol number. So this is what to do. Now let's look at how to do it in this SAD part. Endpoint holds SA state in security association database. When sending IPsec datagram, R1 accesses SAD to determine how to process datagram. When IPsec datagram arrives to router 2, R2 examines SPI in IPsec datagram, indexes SAD with SPI, processing datagram accordingly. So this is how things work here. Okay. Summary is IPsec services as follows. Trudy sits somewhere between R1 and R2. She doesn't know the keys. Questions are, will Trudy be able to see original contents of datagram? How about source destination IP address, transport protocol, application protocol, flip bits without detection, masquerade as R1 using R1's IP address, replay datagram. So in order to actually prevent this, we have to use internet key exchange protocols, okay? So, but as you can see here, Trudy, you cannot do anything if you already established the connection in a good way, because you are using AES, and the Trudy doesn't have the secret key. So you are encrypting everything, so Trudy actually won't be able to perform these attacks, okay? Let's move on to internet key exchange, because we already mentioned that we had to have secret keys to perform these processes. The previous examples, there were manual establishment of IPsec SAs in IPsec endpoints. So when you're creating VPNs and so on, you manually put your secret keys there. So this is how everything works. So as an example is here, like SPI index, this number, source IP, destination IP, protocol ESP, encryption algorithm triple des CBC. As you can see, HMAC algorithm MD5. The book insists on MD5, but you shouldn't be using it. Even I don't, recommend using triple des, and NIST will remove it from the standards in 2024. I mean, it is currently secure if you are choosing your secret keys in a correct way, in a random way, but still, there's no need to use something worse than AES. Okay. So you have your encryption key here and HMAC key here, so you manually can put this. Okay, manual key keying is impractical for VPN with hundreds of endpoints, right? You have to manage all of them. Instead, use IPsec IKE, internet key exchange. So these are actually some methods to perform key exchange. But let's see how this works. Authentication, prove who you are with either pre-shared secrets or with public key infrastructure where you use certificates. Okay. So instead of manually putting secret keys everywhere, you can agree on a pre-shared secret and then use it to generate new keys and so on. Or you can simply use your public key infrastructure where everybody has public and private keys. So you can use those public and private keys to perform key exchange. So for the shared secret, both sides start with secret, run IKE to authenticate each other and to generate IPsec SAAs, one in each direction, including encryption and authentication keys. For the PKI, both sides start with public-private key pair certificate, run IKE to authenticate each other, obtain IPsec SAAs, one in each direction, similar with handshaking SSL TLS. Okay. IKE has two phases. Phase 1, established bidirectional IKE SA. So this is different from IPsec SA. In the phase 2, this security association is used to securely negotiate IPsec pair of SAs. Phase 1 has two modes, aggressive mode and main mode. Aggressive mode uses fewer messages. Main mode provides identity protection and is more flexible. IKE message exchange for algorithm secret keys, SPI numbers. So this is the summary. You can use either AH or ESP, but as I mentioned, almost nobody uses AH because since you already have the service, I mean, if all you need is integrity, then you should use AH. But if you also want confidentiality, you should use ESP. IPsec peers can be two end systems, two router firewalls, or a router firewall and an end system. Okay.